This presentation is on Xgboost, which is a winning algorithm. In this presentation, I'll talk about why it's such a good algorithm for predictive analytics. Now, Xgboost is short for Extreme Gradient Boosting and is a open source machine learning library. It was developed in 2014 by Dr. Chen from the University of Washington, and following that it became quite popular. It's widely used in machine learning competitions in various industries. It's an example of an ensemble algorithm, which is a method that combines multiple predictive algorithms together. And ensembles combine multiple similar or weak learners into a strong learner or algorithm. Xgboost is an example of a boosting ensemble algorithm. This diagram shows ensemble learning. The homogeneous ensemble method means that the algorithms used are all the same, such as all decision trees. And we're going to describe bagging versus boosting on the next slide, but heterogeneous ensemble method means that you're using different algorithms to come up with basically an average prediction, but take advantage of the attributes of different algorithms, and that's called stacking. And this diagram on the left is bagging. An example of that would be random forest, where you take random aspects of decision trees, and in a parallel fashion, you average the results and come up with basically, like crowdsourcing, you come up with an opinion based on all the decision trees. Boosting is different. It's sequential. You start with one tree, and then you learn from its mistakes as you go along, and you continue to improve the model until you get to the point where you want to say the model has finished predicting, is complete, and you're going to use that. So XGBoost is an iterative process. Each subsequent model pays attention to the data points and errors made and keeps improving along the way to get the best model. It scales to large projects so it can handle big data, handles missing data better than many algorithms, and better than many other boosting algorithms. It can be used for classification and regression. It can be used also for class imbalance, which makes it also better than most algorithms, and it's fast. Some of its positive attributes that we haven't covered is it includes model regularization. L1 regularization, also known as lasso or lambda, penalizes the model's coefficients, particularly the ones that are weak coefficients, leading to simpler models by forcing some of those coefficients to become zero. Therefore, it gets rid of the noise in the model. L2, also known as ridge regression or alpha, is similar. It penalizes the squared value of coefficients, which means they don't go to zero and you don't get rid of them, but you minimize the weak actors, if you will. Regularization reduces overfitting, leading to simpler, more generalizable models. It also reduces something called multicollinearity. When two predictors are highly related to each other, such as BMI and weight, you don't tend to need both, and this improves the model. Also, XGBoost can handle linear and nonlinear relationships. In the lower left and in the middle image, you see a linear relationship in the first with an upward trend and the second with a downward trend. But in the third image that says no linear relationship, you notice it's a curvilinear, a curved relationship. An example of a linear relationship is BMI and weight. An example of a nonlinear relationship is BMI and mortality, where the relationship is a U-shaped curve. Also, it should be noted you can adjust the hyperparameters of Xgboost. Hyperparameters are those features you can adjust as opposed to parameters that you can't. But this is a way to improve its performance. This is also known as HPO, or hyperparameter optimization. You can use grid search or random search, which are both are algorithms that basically find the best model as it just goes over every combination to find what gives the best performance. You could also do something called early stopping, so that when the optimal results are achieved, you're done. You can limit the number of trees used, and you can prune the depth of trees. These are examples of current boosting algorithms, starting with Xgboost, that was the first one, and then other gradient boosting, Xgboost, LightGM. You've got CatBoost, which handles categorical data, stochastic gradient boosting, and HPBoost, high performance boosting. It does have some limitations, however. It does require more computational power due to the fact that it's sequential in nature, and that some boosting algorithms they are prone to overfitting, but less so with Xgboost. Categorical variables need to be converted to numerical variables, with the exception of CatBoost that will handle category variables. And you do that with methods such as one-hot encoding. And you need a moderate amount of data for Xgboost to be effective. I'm going to mention a warning, and that is the no free lunch theorem that says despite many positive attributes, Xgboost and other algorithms do not always win the prediction contest. So the theorem states that no single algorithm is always best, and no single performance parameter is always best. This is an example of using Xgboost using Orange Data Mining, a data science platform. You can see all the different algorithms I'm using and running, and lo and behold, logistic regression has the best performance. That's largely because this is a small data set with only like missing data points. It's linear, the relationships are linear, it's a very clean data set. So in this case, logistic regression performed the best. So in conclusion, Xgboost is a high-performance ensemble machine learning algorithm that performs well for classification and regression. It's important to know why it performs well so you know what to expect. It's also important to compare it with other algorithms for prediction as well.